No, Torbjörn.
Okay. All right.
Yes.
Okay.
Keep going, sir. If you want, if you want to repeat anything to be recorded.
Oh, not really. I mean, I'm not sure if you circulated the address to my web page. Did you? Or
We did.
Yeah.
Yes.
So there is a link you can click there and get the information about me. So I don't plan to say more about that, if it's all right with you.
Yes. Thank you.
Okay. Shall I start? It's been a while since I used Zoom, but
Yeah, you can share your screen. Do you see this thing below?
sure. Yeah.
Okay.
So do you see that?
Yes. Yes.
Good. All right. So the Prolog Trinity ecosystem. Well, designing an architecture for an entire ecosystem sounds crazy ambitious, I suppose. But since I'm retired, I'm allowed to attempt something crazy. That's how I see it. I'm building on top of technologies that these people have developed. The two people on the left need no introduction. Here, the man in the middle is Joe Armstrong, who invented the Erlang programming language. And then we have Tim Berners-Lee, who invented the web. And then David Harrell, the inventor of a visual programming / specification language called state charts. Of course, they were not alone in inventing these technologies. Many other people evolved the IDEs into the shape they have today. For Prolog, for example, we have the 15 founders of logic programming, some of you who are here today. So I guess it's more correct to say that I'm walking in the footsteps of those who have been walking in the footsteps of these 5 inventors. So here's the Trinity itself, the Prolog Trinity ecosystem. It consists of these 3 entities: a language, WebProlog, Prolog agents, and the Prolog Web. This is on a very high level of abstraction, obviously. The arrows between them are meant to indicate the many interdependencies that exist between the entities. The Prolog Web is populated by Prolog agents. That's one interdependence. And the Prolog Web also provides, in the form of a distributed Prolog database, some of the knowledge that such agents need to do their thing. Prolog agents in the Prolog Web environment interact with other Prolog agents using WebProlog as, if you want, their language of communication or agent communication language. The Prolog Trinity is actually an instance of another interesting Trinity, and more on a even higher level of abstraction, where you have language agents network. And that could be exemplified by this meeting, actually. we are all agents here. We have at least a temporary here, social network, and we use a language, a lingua franca, English, to talk to each other. Now, let me expand the Prolog Trinity in the three most important directions into a mind map. So we have Prolog, we have WebProlog, which is an extension of a subset of Prolog, and in fact, an extension of a subset of isoprolog. WebProlog also borrows a lot of ideas from Erlang, the Erlang programming language. Then we have Prolog agents. There are two kinds of Prolog agents in this ecosystem. There are actors and there are nodes. And actors come in different types. There are top-level actors, there are state chart actors. In fact, there are several other actors that I won't have time to talk about today, such as supervisor actors and server actors. Those things, those behaviors are borrowed also from Erlang, who talk about behaviors. And then we have the Prolog Web. It's not an island. It extends the traditional web. It is, one could argue, somewhat similar to the semantic web and can be easily interfaced with that. All right, so today I'm going to talk about some of these things. I won't have time to talk about state chart actors. I won't have time to talk about the semantic web, how that sort of supplements or supplements the Prolog web. I won't have time to talk about the agentic web or multi-agent systems or embodied conversational agents. But I'll talk about the other stuff here. So you could imagine with this kind of technologies combined that it could become a kludge. It's very eclectic. I can certainly see that, but it's principled. And I tried to argue, but I'm not sure I'll be able to show that it's very principled. And it's very coherent. I think you have to read the book manuscript, to understand why I dare to say something like that. All right, I delivered just 3-4 weeks ago for the first time in several years, 2 deliverables. A book draft, some 350 pages long, and a proof of concept implementation that you can try out on the web. It serves as a demonstrator of the concepts that I'm talk about today. Both are work in progress. It's a draft, the book, but the demonstrator also needs work. In particular, I think the tutorial needs more work. Okay, another view of the Prolog Web is this. So the boxes here, they are nodes. Each node has a shared a shared Prolog database. They also have, in the form of these smiley emojis, they are actors, all right? There are 5 nodes. There are 4 clients to this partition of the Prolog Web. One actor is actually running in one of the clients, namely this browser here. Okay, so just like the web, this is distributed. There are the connections here are the kind of connections that you have on the web, connecting clients with web servers. So the nodes are web servers, can be built as web servers, but they also contain a runtime system for Prolog actors. So it's distributed, it's decentralized, it's open, well, somewhat open as the way usually is. So here's the anatomy of a Prolog node, because I already said something about the actors and the shared Prolog database. There is also a node controller, and there are web APIs. There are actually 3 web APIs that the most powerful of these nodes can support. There's a stateful WebSocket API, there's a semi-stateful HTTP API, and a stateless HTTP API. The actors, they kind of look simple, but behind the smile here, there's some structure. So an actor, it's the same kind of actor that Erlang uses. Erlang is an actor programming language. So there's a mailbox that stores incoming messages, because clients or other actors can send messages to an actor. There's a receive operator that selects and processes messages from the mailbox. There's a send operation that can send messages to other actors, asynchronous message passing. And there is a spawn operation for creating other actors. Finally, an actor has a private Prolog database. So there are actually 2 databases here. The shared Prolog database that belongs to the node, and each actor also has a private Prolog database. So there are built-in predicates in WebProlog. The names are borrowed from Erlang. It's a good idea to stick to Erlang names for predicates and things like that as much as possible. So just like in Erlang, it's called spawn, the predicate, you spawn other actors. This that looks like the cut in Prolog is not the cut, but in Erlang and in WebProlog, it's a send operator, but you can also use send like this. And there is a receive operator as well. These are the main operators. Okay, There's a built-in message as well that some Prolog actors send when they terminate. All right. So here's a long quote that I don't expect you to read now, but it's from this paper, 50 Years of Prolog and Beyond. And I think you have probably read, and some of you have authored it too, I believe. So if we have these essential and important features of Prolog and combine them with the essential features of Erlang, then we get the essential and important features of WebProlog. And the essential features of Erlang, that's the ability to execute a large number of active processes concurrently. It's the ability to use message passing for inter-process communication, avoiding mutable shared memory and locking issues. And it's the ability to support network transparent concurrent programming, where actors can create other actors on remote computers and start talking to them. So what you get is a multi-paradigm language where logic programming, the logic programming paradigm is sort of combined with the actor programming paradigm. You can have first-class top-level actors. You can have real-time interaction over well-defined protocols inside nodes, but also in between nodes and in between clients and nodes. There is fault-tolerant process management, what the Erlang people refer to as let it crash. Instead of complicated things with error, other can catch and throw and things like that. You just let a process crash, and then you have a supervisor that starts it up again if things go wrong. It's also an effective software development methodology. So one thing I don't really mention here is the fact that concurrency can be used to make things more efficient. And in Erlang, that's not the main purpose. The main purpose is this fault-tolerant process management and also this software development methodology. That this is actually a quote by Joe Armstrong. By decomposing complex problems into smaller independent tasks, concurrency allows for modular system design. Now, this I just told you about could work very well for a general purpose programming language. No doubt about that. But I'm targeting the web and web programming instead. So this is Tim Berners-Lee saying that the essential process in webizing is to take a system which is designed as a closed world and then ask what happens when it is considered as part of an open world. And the web, of course, is a very open world. Erlang don't work in an open world. They only make distributed programming inside very private compartments. So what's needed then in order to webize Prolog? It's to introduce URLs, if you want, into the ecosystem, exploit existing web infrastructure, such as HTTP and WebSockets and JSON and things like that. And also make use of existing means for security, perhaps making the language not so powerful so that it can hurt the machines on which it runs. It's important on the web to ensure that we can scale it up, and we must support web application development, ensure fitness to web culture, and on the web, things must be standardized. It's time for the first small example of how you program in this language. So here's it's just one clause defining a count actor, an actor that can keep a count. So the important thing here is the receive operation. It listens for messages of this form, count or stop. If a count operation, if a count message shows up with from a PID. Oh, I just recall that I didn't say that an actor, when you spawn an actor, it always gets a process identifier. So if a process spawns this count actor, this from here will be instantiated to PID from the parent process. And then we calculate, we compute the count, and we send to the parent this term that represents the count, and then we call this recursively. So you see the actual count is passed around in the argument of this. Okay, so let's try this. This is how you spawn this actor. And there's an option monitor here that tells the spawn operator that we should, when the count actor terminates, it should tell the parent that it has terminated. So there's a PID resulting there, and then we can call self, which gives us the PID for the parent of the count actor. And then we can send to this PID, this message, which will be captured here. And we can receive then the count, and we can do this again, and then we can stop. And what we get, if we call flush, which sort of removes and show us the all the messages that are in the mailbox of the parent process, which is this that we're running here. So the shell got count 2 and this down. True here means that the termination was normal. All right, we could also, since this is network transparent concurrency, we can use an option node here and point to another node. And we get a more complex PID. We send count, this count message to that, and we exit, we let it die, and we get back that. Now this assumes that this node n.org actually contains this source code, otherwise it wouldn't work. And what we can do, though, is to use another option, load text, and send this program along, and it will work just as it did before. Okay, so here's another example. There's two actors playing ping pong. And when we start it, it looks like this. I see the time is running, fly like an arrow. So I have to speed things up, I suppose. This is Joe Armstrong again. He read my manuscript, an old manuscript from 2018, and this is what he said. Reading the code was fun. I had to do a double take. Was I reading Erlang or Prolog? They often look pretty much the same. And it's true, isn't it? If you look at these two programs, at least very quickly, it's kind of obvious that Erlang was actually built. The first Erlang compiler was built using Prolog, and it shows. There are many similarities. They are both dynamically typed. They use pattern matching, recursion, assign once variables, but Erlang doesn't support unification. The receive clause look nearly the same. But as for difference, Erlang is a functional language that allows functional nesting. You can see it is here, for example, or here. And right. This is another person that you most likely recognize, Richard O'Keefe. He was kind enough to read a paper that I wrote for an Erlang conference. Actually, I was admitted to an Erlang conference in 2019. He said in an Erlang programming mailing list, I would prefer multi-threading in Prolog to look as much as possible like Erlang. I certainly agree with him. So I don't expect you to read these programs. I just want you to look at the comparison in size. They both do, although the names are somewhat different. I call this program parallel. So the idea is calling parallel, this predicate parallel, with a list of goals should succeed with variable bindings if all goals in the list succeed. It should fail as quickly as possible if any goal fails, and rethrow any errors thrown by a goal also as quickly as possible. Now, this is John Willemacker's implementation of concurrent. It takes 3 arguments instead of 1, but it does really the same. I could also add some more arguments for options and things to my parallel program. But they do exactly the same. Now, this is not a criticism of John's implementation. He's a very good programmer. And it's the right implementation for SWI Prolog, ISO-ish thread predicates. But this shows you what the actor model with receive and things buys you in terms of expressiveness. I should also say that the best way, and the way I use now to implement this parallel, to implement WebProlog is to implement it on top of the ISO-ish thread, that standard that didn't become a standard. At least not yet, probably never. All right, so here's a top level actor. It's an actor with a built-in protocol. That's what it is. The protocol, let me say first what the purpose is. You can create it, you can send it queries and getting answers in return. Just one answer if that is what you want, or as many as you want. And some actors, you can create many top-level actors. They can run inside one node, or they can be used in a distributed fashion. Here's a state chart specifying the Prolog top-level communication protocol, as I showed. I'm not going to say anything about that, but just say that it's much better to present developers with a set of high-level predicates, such as these here, suitable for controlling the top-level process. And here are the built-in messages that you receive as the result of evaluating queries. Here's where I have to speed things up a bit. So suppose you have a node like this with a shared database here, node controller, and then you decide to go from this client, you want to go to n1.org. So what happens here is that the browser gets some JavaScript and establishes a WebSocket connection to the node. Then there is a JSON command talking to the node controller, and it says top-level spawn here, and the node controller does that. So a top level appears inside the node, and the node controller sends, okay, I spawned a top level actor, it has a PID 93, etc., etc. And that, sorry, I took the wrong. That results in this welcome message and the usual prompt. And then if the user here wants to assert this clause There's a command top-level call. You have to send along the PID and the goal, of course, and then you say, I just want one solution. You limit the number of solutions to one. You always do that because you want to make it as easy as possible to write your terminal code in JavaScript. Okay, so the process, the goal is processed. The private database is populated with this clause, and you get this back true, right? And then again, you want to ask Q of X, was that right? Okay, so I want another one, top level next, all right, and then when you call greetings here, you get just pushes of results back until you abort this query. Now, here's something you can do too. You can spawn a count actor. Right, so the actor here was spawned. And then you can talk directly to that actor. Here's another example where you play ping pong between two nodes. You have to start by creating a top level from the browser. Then when you run start, there's an actor pinger here and a ponger in the other node. So you get only half because this can only print, this one cannot print to this in this version, but might work in the future. Now, that was a WebSocket API, a stateful WebSocket API that can push data from the node to the client. There is also a stateless HTTP API. And that's, in a sense, even more important, at least in some circumstances, than the WebSocket API. But the stateless HTTP API is actually built on top of the stateful WebSocket API. Or not really, but on top of top-level actors. I don't think I have time to look at all this, but on top of this stateless HTTP API, you can implement a predicate RPC that allows a process running on a node A to call a goal in the Prolog context of another node B, taking advantage of the programs and data being offered by B, just as if they were local to A. And here's the signature. It's very simple and easy to use, and there's no observable concurrency involved, so that is what makes it simple and easy to use. And it can, as I said, be implemented on top of the stateless HTTP API. The original idea was actually John Willemacker's. He never implemented it, but I did, and I kind of like this predicate a lot. Here's an example. We have two nodes, stateless HTTPI in between. And you can see if we call mortal of whole here, we get we do a get request. Here's an actor starting up and terminates again. An answer gets back to Socrates. And then no connection. We want the next solution. So the difference here is that in the first query, the offset was 0, but here it's 1. Now you can ask yourself, is this a new actor again who's computing this second answer? No, it's not, because the first actor has actually been cached in between. So the second clause for human here says that we should use RPC to this node. Another actor is created there. The default here is that all the answers to this query, both these answers should be returned. But no, sorry about that. There we are. Now, this actor, again, sent a message, JSON message back to the browser, and there's another query. And again, it's still the same actor here. It was just sleeping in between. It was cached. And there you have it. Now, let's pretend that you have a much, much bigger database, billions of clauses of human. How can you do that if you expect this RPC to receive all the solutions to this query human here? The secret is that there is an option here to RPC that limits the number of solutions that you will grab from this node. So by doing that, it's still complete. You can sort of do the same thing all the time, but and it will work. Okay. So the language and the nodes, they come in different profiles. So first we looked at all these predicates here that are the ones that are inspired by Erlang. And that's the actor profile. The isobase profile is the one we looked at in the most recent example, where we could use RPC and the stateless HTTP API. Now, it's easier to implement a node that can handle only the isobase profile. It's much harder, of course, to implement a node that can handle the actor profile. So that's one reason why this splitting of node profiles of nodes into different profiles. So for the stateful WebSocket APIs, there are pros and cons. The pros are that clients can have almost full control of their own WebProlog processes on a node. And it also supports full Prolog, including constructs with side effects such as I/O and database manipulation. And it supports predicates for spawning processes and sending and receiving messages. There are cons too. Scalability might be a problem because clients tend to tie up parts of nodes resources for as long as a session lasts. So access may have to be restricted. But this API is important to have for certain applications. If you're building multi-agent systems, for example, I think in many cases, a persistent bidirectional exchange that the WebSocket API can do is good to have. Also for building embodied conversational agents, which is one of my interests, it's really good to have that kind of conversation. And of course, for fast-paced, first shooter game, web-based games and things like that. The stateless HTTP API also have pros and cons. It supports the very elementary getting one at a time solutions and on backtracking and the kind of interactions you see here. And also, instead of having each client tie up part of a node's resources for as long as the session lasts, it can release them as soon as it wants. The connections are not persistent. And also, which is one of the reasons that the World Wide Web could scale to this, what we have now, is that statelessness makes caching of responses by queries to queries by intermediate systems possible and often worthwhile. Now, the cons is that there are certain things we just cannot support. For example, we cannot abort a query. There's no way we can do that with a truly stateless HTTP API. We cannot support I/O over this kind of API or database updates. So it means time limits must be imposed because we cannot abort queries, and the language must be restricted. Suggested uses here is for distributed knowledge bases, basically. All right, so I'm sort of have 4 or 5 slides left, and they will be fairly quick, I think. Now, here's the situation. Now, I would say, the demonstrator is implemented in SWI Prolog only. And it's a testament of the power of this implementation that you can do that. Now, when I read this 50 years of Prolog and beyond paper, I was in particularly interested in this SWOT table, where weaknesses and threats. Threats is not spelled like that. Oh, never mind. Where it said that a fragmented community and a fragmented Prolog systems landscape leads to problems with portability. And the systems and the community is really fragmented, and it can be shown by just pointing at all these different logotypes for these systems. A proposal then would be to aim for interoperability across systems using WebProlog as a lingua franca. It's even more ambitious than building just an ecosystem using only SWI Prolog, of course. So if you imagine such an ambition, you could have something like this, where different nodes can be implemented on top of different systems. You can also imagine taking it one step further, not limiting yourself to the Prolog tradition. So it points to the possibility of a logic programming web in a broader sense. So this symbol here, for example, that's CPLINT, which is probabilistic logic programming by Fabrizio Riguzzi. It would work very well over just the isobase or isotope profile of WebProlog, where you have perhaps only the stateless HTTP API. And then you have logical LPS, logical production systems. That I think is kind of interesting to think about building a real multi-agent systems running LPS inside different, not only different nodes, but also just different actors. Okay, so this is my last slide. It's similar to the first slide. I just want to point out that if we want to go this way, having a standardized lingua franca WebProlog that could, bring the community together and allow every system to make use of the capabilities of any other system. This language will have to be standardized. I just think that should be done in W3C, in cooperation, in a liaison, perhaps, with ISO. Okay, thank you. That's it.
Thank you very much. Okay. Yeah, thank you very much. That was an interesting talk. I'm not, yeah, close. We do, it's already 10, but we do have time. There's an echo. For questions, any questions? Did you tell Jan about these results yet, or not?
Yeah, yes, I did, yes.
Okay.
He's interested, but he's very, he kind of likes Swish, and Swish is based on a software, a library called Library Penguins that I actually designed back in 2013 or something. I'm not happy about that library. I think it has the wrong design. So this stuff that I've been showing you today is actually how I think it should have been designed.
Mm-hmm. Okay, well, thank you again, and I'll be in touch about the next meeting. And of course, there's a website at the beginning of this talk if anybody wants to.
Can I ask you?
Yes, sure.
I noticed that I have had very few visitors to my demonstrator, just one visitor actually. So maybe that's if you provide a demonstrator like I've done, maybe that's not interesting for the community. I advertise this not only in the website, in Prolog, the general Prolog site that where you probably found it, but also on the SWI discourse site. So I just wonder, maybe it's a waste of time for me to provide a demonstrator.
You mean a website like the one you have? It's not that popular.
Yeah.
That's what I'm saying. Okay. I mean, I think the basic reason is the one you reflected in your last slide. We are a fragmented community doing different things. But on top of that, we also have this now sort of competition in disadvantage against LLMs, which are presented as the new agents. And that's another thing we have to address. But I mean, I definitely love the idea of having an integrated language based on logic. Prolog as the general language, not only to represent knowledge inside a knowledge base, but also to communicate among agents. That's powerful. I mean, you showed that, of course, what Jan is going to answer, I guess, is that you are assuming a framework, a pre-existing framework, all these actors and things. That's why you can get a small description of an actor, because most of the work is being done by the implementation of the protocols, right? So that's what makes it simpler. But that's a good argument anyway. That I would wonder if you wanted to. I mean, one of the things you are doing that we are also very interested in is teaching. That this kind of platform you produced is a teaching environment, basically, when you combine more than one idea, and that's going to be useful, I believe. So I would say, hold on, sir. We are going to get more help, I guess, and we can offer you the visibility of our modest channels, like the one in YouTube, and also this course. But I wouldn't let myself be distracted by the fact that not many people is coming now to your site. It's going to change, I believe.
No, I'm sure you're right. Yeah, teaching, since I'm not doing any teaching myself any longer, is not my main interest, of course. But you're right that this could provide a playground that allows students to exercise, to use not only logic programming, but also actor programming.
Yeah, you said that you said that the paintings, the platform that we have in SWI Prolog is not well designed, but they have hundreds of students every day using Swish, which is based on paintings.
Yeah.
So
absolutely,
me,
yeah.
very useful.
I'm happy about Swish. That was actually my proposal too. I implemented this. I think it was 2013. Yes, as no, that was even earlier, as an homage to SWI Prolog on its 25th birthday. So I think, and then of course, my implementation was crappy. So I went down to meet with John in Amsterdam and sat with him for some time. And he's such a great programmer, so he could really build a useful system from it.
Yes.
But after a while, I got sort of disappointed somewhat in John because he didn't want to replace the bad design of the library penguins with my much better design. So, yeah.
I think he's letting it crash.
Yeah, yes. It's actually he had lots of problems that he needed to solve. Those problems have gone now because the design is better. Yeah.
Thank you.
No, I'm wondering, we have an annual meeting, and the one of this year is coming up soon, so there's no time. Papers have been accepted, but maybe you would be interested in writing an article about applying this to teaching and submitting it to our next Prolog workshop, Prolog education workshop.
Yeah.
I don't even know when that is or where it'll be, but it's soon it's going to be decided and published, so that might be an idea.
Another, just a final question. If any one of you have students that could, take a look at my book draft and my demonstrator, I would be very interested, and I could sort of supervise them if they would need to write a paper about it. So, yeah, it's just one thing. All right. Thank you.
Thank you
very
again
much. Thanks for having me. All right. Okay.
See you all.
Bye-bye.
Thank you very much. Bye-bye.
Thank you.
Bye.
Thank you very much.